last week. Our aim in this chapter is to learn about the Laplace transform so that we have it as a solution method for solving certain types of differential equation. Remember, the types of differential equation we're going to be able to solve are so-called linear ordinary differential equations with constant coefficients. Ordinary meaning the unknown function y is a function just of a single variable, so there's just ordinary derivatives appearing, not partial derivatives, ordinary derivatives. Linear means none of those derivatives are done anything funny with. No, we don't have different derivatives multiplied together. We don't have single derivative raised to any power. Okay? If a derivative occurs, it just occurs there in the equation as a term added up in the equation, maybe with a constant coefficient multiplying it. So the unknown function y and any of its derivatives may appear there, multiplied by constant coefficients. But then you may have this non-constant term, this function g of t, some other function appearing normally on the right-hand side of the equation. Those are the kind of things we're going to be able to solve, providing we can apply the Laplace transform to it. Providing that this function g here is one that we understand well enough to be able to take its Laplace transform. What is the Laplace transform? Well, we spent a few lectures talking about that. It's this integral transform here in equation 2.4. We explained it as something analogous to constructing a power series, which is a function of x, out of a sequence of coefficients x. It's a somewhat analogous operation where you take not a sequence of values, but a whole function's worth of values. A whole set of values f of t for every t between 0 and infinity, as opposed to just a sequence of values an for every integer n between 1 and infinity or 0 and infinity. That sequence of values you can bundle up into a power series using a summation of the coefficients times the power of x. Here we're doing something similar. We're bundling up all those function values, summing them all up, meaning we're doing an integration from 0 to infinity of those function values, and they're multiplied by effectively a new variable s raised to the power t, except it's normalized in a certain way, and it's presented as the exponential e to the minus s itself raised to the power, then raised to the power t, but that's using rules of indices, that's equal to e to the minus s times t. That's the Laplace transform of the function little f. It's called variously, we might call it the function capital F of s, partnered with little f. We might stick an overline over the original function name little f, or we might indicate the presence of the Laplace operator there as a script L, a curly handwriting L. Script L applied to the original function f of t. The thing you get is a function not of t, but it's a function of this new variable s. You don't get a different value here for different values of t. The t is integrated out, summing up all the values of t. But you do get a different value from the transform for different values of s. So it's a function of s. So continuing the recap, in the previous lectures, we started working through properties of the transform, and also working through transforms of particular functions. The transforms of particular functions are all gathered together for us on what we refer to as the table of Laplace transforms. So the table of Laplace transforms is this two-page sheet here. This is the actual extract from the standard faculty formula booklet that you'll have in exams and so on. This lists a lot of standard functions down the left, functions of t, together with their corresponding Laplace transforms down the right-hand side. We can use this in both directions. So given a certain function of t, we can find it here on the left, we can read off its Laplace transform. But in the other direction, given a certain function of s, if we can find it here, then we can read off its inverse transform by moving to the corresponding thing on the left. Also summarized on the second page of the table are various properties of the Laplace transform. Not transform of individual particular functions, but more general properties of it. So we've proved basically a lot of these so far. The first one was linearity of the transform. The transform itself is a linear operator. It gets that linearity property because it's based on integration, and integration is linear. So if you take a Laplace transform of a linear combination of two functions f and g, what you get is the same linear combination, alpha and beta as the coefficients, same linear combination of the individual Laplace transforms. Okay, so that's nice to know. We want to take a Laplace transform of a big sum of different things. You just take the transform of each individual bit and add the results together. That's the property of linearity. Second property was what happened if you differentiated the transform. Looking at this on the right-hand side, if you take the derivative of a transform, what you're doing is, in effect, you're taking the Laplace transform of t times the original function f. Okay? So capital F is the transform of the function little f, and you differentiate the transform with a minus sign. That's the same as taking the Laplace transform of t times the original function f. That can help us. This property here is crucially kind of important for the whole enterprise. Okay, we want to be able to solve differential equations. Differential equations, by definition, feature derivatives of the unknown function. This property here shows us exactly how the Laplace transform of the derivative of a function relates to the Laplace transform of the original function itself. Okay. So x here you can imagine as being the unknown term in a differential equation. How do we deal with the Laplace transform of the derivative of x? Well, we can deal with it in this way. It's simply s times whatever the Laplace transform of little x was, minus this constant term, which is the initial value of x. So that's kind of the last thing that we proved when we spoke last time. And then we also looked at, okay, that deals with taking the Laplace transform of the derivative of x. You can just apply it again and again and again to deal with higher order derivatives. You don't need to prove anything new. You just need to run that property on itself, substitute it into itself, however many number of times, and we get this general result, which tells us this is what we need for tackling differential equations, as we're about to see. This allows us to understand the Laplace transform of any order derivative of x in terms of the Laplace transform of x, power of the new variable s here, s to the power n, and then what are we looking at here? Okay, there's complicated indices around, but what we're looking at is a polynomial in s. Polynomial in s of degree goes up to degree n minus 1. And the coefficients are these numbers xi, x subscript I. That's just a shorthand notation. Okay, that's just a shorthand notation for the initial values of the various lower order derivatives of x, lower than the order n that you're focusing. Okay. Okay. Any questions about any of those properties that we quickly reviewed there? Okay, we're about to put them all together now to explain how it is we go about solving the differential equations. Okay, so let's turn over the page to page 48. Okay, so here are a number of numbered steps which tell us how to solve one of these differential equations. There's a worked example below. And I've got some more examples to work through here on the board as well. Okay, so let's look at the method. So we want to solve an object like this. Okay, what is that? It's a differential equation for the unknown function y. We'll assume that g is some function which is known to us, and that we're able to deal with g. We're able to take the Laplace transform of g. Okay, the first step is to just take the Laplace transform of the whole equation. Say that the Laplace transform of the left-hand side is equal to the Laplace transform of the right-hand side. Okay. So transform the whole equation. Now what does that mean? Well, okay, you'll have to take the Laplace transform of the function g, fair enough. Over here on the left, you've got a linear combination of various derivatives of y. The zeroth derivative of y, namely the original function y itself, and its first, second, all the way up to its nth order derivative. But they're all added together. We've got a linear combination of those with these constant coefficients, ai. Using the linearity of the transform, we say the linear transform of the left-hand side is just the linear combination of the individual Laplace transforms. Okay, the function y is unknown to us at this stage. We're trying to solve for it. So we just use a symbol to represent the Laplace transform of y. Conventionally, we'll use a capital Y. Capital Y to represent the transform of the function y. We don't need new symbols to represent the transforms of the other derivatives, because the property of the Laplace transform of derivatives we just looked at relates the Laplace transform of each of these terms, relates it to the Laplace transform of y. So this capital Y we're introducing for the Laplace transform of little y will turn up in all these terms, together with polynomials in S, whose coefficients are initial values of y and its various derivatives. Typically, in an ordinary differential equation problem, typically you are provided with these initial values. Because a differential equation on its own probably has multiple solutions. It probably has a family of solutions that are parameterized by various parameters. And you can only single out a single unique solution when provided with some extra information. The beginning value of the function, or the beginning value, the initial value of the function, and some of its derivatives, which in a physical context would equate to knowing the initial position of the particle, say, if the function was governing the one-dimensional position of something in some kind of physics problem, knowing the initial position or velocity and acceleration. So if y was the position of something, the derivative would be its initial its velocity, the second derivative would be its acceleration. So knowing those initial values, if the differential equation was governing the evolution of the position of that thing, then knowing those initial values, solving the differential equation would pin it down to a unique solution. So typically we'll be given some initial conditions which we substitute into the transformed equation just to get rid of those unknown constants, so to speak. We then have, okay, I'm calling it y bar, I'm calling the transform of y bar there. We then have a kind of algebraic equation for the transform y bar, which we then solve. We solve for y bar, and we get the solution for y bar as a function of s, some kind of function of s. And the very last step is to take that specification for y bar as a function of s and do the inverse transform. The inverse transform takes your function of s and gives you back a function of t. Because we're taking the inverse transform of y bar, we get back the original function y of t as a specified function of t. We should get back the solution to the original differential equation. Okay, those are the steps spelled out. So let's start looking at some examples. Okay, we really need to see this. Really need to see this at work in order to understand it. Okay, I know it's spelled out there, but I'm going to write it out anyway, just because it kind of helps the mind to work as we look through it. And I've got some other examples as well. So let's look at this example 2.6. We don't necessarily have to take this one down since it's in the book. So here's the original differential equation, d2y dt squared, and minus 5 dy dt is 4y equals 12. So step one is to take the Laplace transform of the whole thing. So basically, Laplace transform of the left-hand side equals the Laplace transform of the right-hand side. Okay, you got an equation, you do the same thing to both sides, you still got an equation. Okay, okay, the Laplace transform of 12, we use our table of transforms. So the Laplace transform of a constant is just that constant divided by s. So it's 12 over s on the right-hand side. On the left-hand side, okay, we can use linearity, first of all. Linearity to say the Laplace transform of all of this is just the transform of this plus the transform of that plus the transform of that. You can transform each individual bit. So 4 times y, what's the transform of 4 times y? Well, we don't know what y is. We're trying to solve for y. So we've got no other option than just to simply indicate the transform of y. Okay? I don't know what y is, so we just indicate here that we've got 4 times the Laplace transform of y. We're going to find this later on. But having named it, having named y bar, we're then able to write down the transform of the other terms in the differential equation in terms of this y bar. Minus 5 times the transform of the first derivative means minus 5 times s y bar minus y of 0. And the transform of the second derivative means s squared times y bar minus s, I often forget the way these go, minus s times the initial value of y minus the initial value of the first derivative of y. It'll allow me to write the first derivative like that. So that's finished. Now, you have to forgive me, that's a 5. The other 5 looking things are s's, so you just have to be alive to that. That's the coefficients 5. The other things are s's. And now you'll notice in the specification of the problem, we were also given initial conditions. So solving this ODE subject to these typical kind of simplest type of initial conditions is that the initial value of both the unknown function y and its first derivative are both 0. In a physical context, if y of t was the position of something at time t, those initial values would correspond to the thing beginning at a certain location, okay, position 0, but with 0 velocity at the start. Y prime of 0 being 0. Now that simplifies things somewhat, because then we know that this is 0 here, this is 0 here, and this is 0 here. So it simplifies the left-hand side. So putting in the initial values, okay, we've got an s squared times y bar, 0, 0, minus 5s times y bar, 0, plus 4 times y bar equals 12 over s. Now you look where we started and you look where we are. We started with a differential equation involving y itself, its first derivative, and its second derivative. So effectively 3 different derivatives of y, all together mixed up in an equation. It's quite hard to deal with directly and solve directly, okay? Because you can't bring together easily the function and its different derivatives. But after transforming it, what we now have is an equation. Okay, there's still an unknown in the equation, y bar. We haven't magically gotten rid of the unknown quantity or discovered what it is. But we got a new equation with this new unknown quantity, but it's very much related to y. It's the transform of y. But it's the only thing appearing here. It's not a whole different thing here or a whole different thing here. It's again just y bar. It's slightly complicated by the fact it's multiplied by various s's. Multiplied by 5s here, multiplied by s squared there. Well, that's okay. That's an algebraic complication, a kind of polynomial complication, which is kind of easier to deal with, easier to make progress with than the different differential operators up there in the original equation. So indeed, we can start factorizing out here. That implies that s squared minus 5s plus 4 times y bar equals 12 over s. And now we can, the solution for y bar is kind of staring us in the face there. This is y bar is equal to 12 over s multiplied by s squared minus 5s plus 4. So that's kind of at the end of step 3. The various numbered steps there were at the end of step 3. We found the solution to y bar. In principle now, we just have to take the inverse transform to recover the original solution y of t. In principle, just take inverse transform now. And indeed, if we allowed ourselves to use algebraic software, we just type that in, type that function in, ask for its inverse transform, and it would tell us what function of t is the inverse transform of that. I'm going to work a little bit more with properties of the transform and the known transform of known functions. So we're going to try and use the table of Laplace transforms for this. So at this stage, we've got y bar as this function of s. So in principle, what we're doing is we're looking down the right-hand side of the table of Laplace transforms. We're looking for that function of s, trying to discover it. But we find that there's nothing here that exactly fits the pattern of that rational function, 12 over s times that quadratic polynomial. We can see elements of that present in various different cases here, but we don't actually see something exactly of that form here. So we need to re-express this. But in order to find this in the tables, in the transform table, we need to re-express it. Using partial fractions. Okay, because we do remember the term rational function is what we use for quotients of polynomials. This is a rational function. It's a constant 12 over a cubic polynomial. There are rational functions in the table of transform there, but they're all of kind of fairly simple type, either just 1 over s plus a, 1 over a linear factor, or 1 over a s squared plus omega squared, so a quadratic without a s term, or 1 over a general quadratic, but where the quadratic is presented in a form of completing the square. Those s plus a squareds plus or minus omega squareds that you see in the bottom third of the table. So at the moment, we're faced with this task now. We have to do a partial fraction expansion on this to discover what combination of those simpler rational functions that it is that we're looking at here. Okay? So thankfully, the quadratic factorizes into y minus 4 times, sorry, s minus 4 to s minus 1. Okay, this will have a certain partial fraction expansion. I'm just going to take the answer to this partial fraction expansion from the notes. The second example I'm going to do has, I'll do the working out to actually find the partial fraction expansion. But you will need to go and revise on how we work out these partial fraction expansions. So let's just take the answer from the notes there. This is 3 over s plus 1 over s minus 4 minus 4 over s minus 1. Okay, so there's a bit of work there to do that. Partial fraction expansion. So once we have those coefficients, what we're looking at now is a linear combination of much simpler rational functions. Something over s plus something else, something over s plus another thing. Okay? Not cubic, not a whole cubic term in the denominator, just linear terms. Okay? Those can all be found on the Laplace transform table. So now we can say the solution we're looking at, y of t, which is the inverse transform of y bar, which will be the inverse transform of all of this. And by linearity, that's going to be 3 times the inverse transform of 1 over s, plus the inverse transform of 1 over s minus 4, minus 4 times the inverse transform of 1 over s minus 1. Okay, so now we can look to our table. And each of those functions there can be found on the table. 1 over s is the transform. 1 over s is the transform of the constant 1, and 1 over s plus something, s plus a, is the transform of e to the minus 8. So this is the constant 3 plus e to the 4t minus 4 times e to the t. So that's those 4 steps we've gone through there of solving the differential equation. Okay? From start to finish, it was transform the whole equation, transform the left-hand side as transform the right-hand side. So we're actually using a number of things. So I should have said a number of justifications here. To get to this step here, we're actually using linearity and the transform of derivatives property. Properties. Okay. How to transform a derivative of the function y and relate that to the transform of y. To transform the whole thing, brought in the known initial values, which simplified it somewhat, then solve the transformed equation for y bar. And in principle, then just take the inverse transform of this. Except we couldn't do that straight away because we couldn't find this function on the table, so we needed to go to a partial fraction expansion because you would find these simpler types of function on the table. And once we found the coefficients there, it enables us to express the solution, y of t, to the original problem as this combination of inverse transforms. You read off the table, so it's this constant and these 2 exponential functions. So that's the solution to the original differential equation. I've got another example here ready that we can discuss, but any questions about that?
The initial value, the main question.
The initial value, yeah, was part of the statement of the problem. They quite often come as part of the problem. It's a typical engineering physics example is you're looking, the differential equation governs the evolution of some kind of system, and the initial value is generally, you know, the configuration of the system at time 0, and you're interested in how it evolves in future time. So typically, those values are provided. Okay, there's a second example there, example 2.7. We could work through. Are we finished with that page? And please do stop me at any point during it. If there's anything you're unsure about, you want to ask about anything. So example 2.7 is to solve the differential equation dy dt plus 2y equals 4. Okay, so simpler. It's only order 1. You've only got a first derivative. And subject to an initial equation and an initial value, y0 equals 3. Okay, so this ought not to be that hard. It should be slightly easier than the previous one, because it's only order 1, whereas the previous one was order 2. Okay, so first step is to transform the whole thing. So the Laplace transform of dy dt is 2y equals the Laplace transform of 4. That implies the Laplace transform, I'll just spell out the linearity here, equals the Laplace transform of 4. So that's true by linearity. Laplace transform of this was 2 times the Laplace transform of y equals the Laplace transform of 4. Now we can read it, we can apply all those Laplace transforms using the table. Laplace transform of 4 is 4 over s. The Laplace transform of y, well, I don't know what y is. I just have to keep it there as the Laplace transform of y. It's a little bit more efficient, rather than having to write curly t, curly brackets every time, to just put an overline over y, just to indicate it's not y, but it's something closely associated to y. All we're doing here is writing y bar as the Laplace transform of y, just to save us writing curly L, curly brackets over it. Then we still got this bit to do, the Laplace transform of the first derivative. You look at the transform of derivatives properties. It's one of those, and it's summarized on the second page of the table. The Laplace transform of the first derivative is s times the transform of y, whatever that is, it's yet to be discovered, minus the initial value of y. And just keep our plus here by linearity. Everybody okay with that step? So that's, yeah, question. Zoom in, yeah. Okay. Any queries about what went on there? So transforming the whole thing, at the same time using linearity and transform of derivatives properties to get to this stage. Now we'll bring in the provided constant, which was the initial value of y being 3. So what have we got here? We've got sy bar minus 3 plus 2y bar equals 4 over s. Now the task is to solve this equation for y bar. It's a lot easier to do than solving the original differential equation. That's the power of the transform. This thing we can just proceed just by algebraic manipulation. Just factor out the y bar, move everything else over to the other side, divide by the coefficient of y bar. Okay? Algebraic manipulation, basic principles. So this implies that y bar is, well, first of all, you have to bring the 3 over. So that'll be 4 plus 3s all over s. And then you got to divide by s plus 2, because that's the coefficient. Well, the s, well, you see, the 3 comes over as a plus 3, and then I just wanted to write it over a single fraction. I didn't want to have 2 separate fractions, so I just put it as 3s over s. Yeah, it's over a common denominator. Then divide across by the coefficient of y bar, which you've left behind on the left-hand side, which is s plus 2. But actually, I'm going to separate it now. So probably a needless complication. So this is 4 over s times s plus 2 plus 3 over s plus 2. Okay, I'm happy to separate that off because I'm able to take the inverse transform of that. This is just a constant over s plus a. That's on the table of transforms, so I'll be able to take the transform of that. You won't find something like this exactly on the table. So it's something over s squared plus 2s. There aren't any entries on the table where the denominator function is s squared, is a square of s plus an s and no constant. So this one you're going to have to do partial fractions on again. Again, the numbers are fairly nicely arranged. Actually, it's the next example. The next example I've got is a kind of a humdinger. Got the full partial fraction show on that. So we'll do that the next lecture. But see this one, partial fractions, this is going to be something over s plus something over s plus 2. Still got the plus 3 over s plus 2 back here. Well, to get the s's to cancel, to just leave you a constant, you have to have the same thing on top and bottom, but with reverse sign. And if you want to end up with 4 here, just have a plus 2 here. 2 times that 2 will give you the 4. So if you got a plus 2 here, you have to have a minus 2. 2 minus 2. And that simplifies to 2 over s plus 1 over s plus 2. Okay? That's our solution to the transformed problem. That's the solution for y bar. It's a lot easier than solving the differential equation. It's just algebraic manipulation, a bit of partial fractions, just to find a nice way of expressing it in terms of things that we can deal with from our table. So now we're ready to just do that final step, to just take the inverse transform, this whole thing. The inverse transform of y bar is just y. The inverse transform of that, we can read it off the table. So now we recover the solution y of t as y of t is the inverse transform of y bar. By linearity, it's 2 times the inverse transform of 1 over s plus the inverse transform of 1 over s plus 2. Linearity property coming in, it's used all over the place. Fundamental property. And those transforms you can take off the table. This is the constant 2 plus e to the minus 2t. That's our solution to that differential equation. Okay, you can check it by taking that function of t, substituting it into the original ODE. You'll be able to confirm that it solves the equation. Okay, I've got another couple of examples to look at. Some more aspects of that when I see you in an hour's time, then in Jeffrey Manton. Isn't that right? We might do yet more kind of workshop work with it this evening. Okay. So I'll leave it there for this morning. So I'll see you again in an hour, then Jeffrey Manton. And we'll take it from there.